If we so wanted, and there's no reason why we have to do this, if we wanted to associate a base with the natural log system, this is just a little aside, and we'll talk about this more perhaps in the learning exercises or in the supplementary notes as need be. But the idea is this. Notice that in a traditional logarithm system, if the base is b, the base is characterized by the fact that the log of b to the base b is 1. Thus, if we use e to denote the base for the natural log, whatever e is, it must be characterized by the fact that the natural log of e is 1. And the reason that I put the word base in quotation marks here is that I would like you to observe that, again, if I have never heard of the word exponent, it still makes sense to say, find the number e such that the natural log of e is 1. In fact, I can give you two interpretations for that number e, and as a byproduct, even show you why the second fundamental theorem of integral calculus is as powerful as it really is. See, the idea is this. To find what e is, all we're saying is take the curve y equals natural log x. Okay? Look to see where the y coordinate is 1. In other words, draw the line y equals 1, where that line intercepts the curve y equals log x. That x coordinate is e. In other words, the natural log of e must be 1. So this is geometrically how I would locate e using differential calculus. If I wanted to use integral calculus, notice that the log of e by definition is what? The integral from 1 to e dt over t. That's the area of this region R. Now what do I want e to be? I want e to be that number that makes this area 1. In other words, I want the natural log of e to be 1. So again, in the same way that one can think of pi as being geometrically constructed, notice I can construct e geometrically. Namely, again, what? I take the curve y equals 1 over t, from t equals 1, bounded below by the t-axis, and I keep shifting over to the right until the area of this region R is exactly 1. The value, the t-value that makes this area 1 is called e. And by the way, notice again the power of what I mean by the area approach. Notice I can start now to get estimates on what e must look like. Let me show you what I'm driving at over here. Let's suppose we take the curve y equals 1 over t from 1 to 2. Now, what do we mean by natural log 2? Natural log 2 is by definition the area of this region here. Now notice that the smallest height of this region, since the curve is y equals 1 over t, the smallest height of this region is a half. And the tallest height, the highest height in this region, is 1. Consequently, whatever the area of this region is, it's less than the area of the inscribed rectangle. It's greater than the area of the inscribed rectangle and less than the area of the circumscribed rectangle. Now, notice that both of these rectangles have base 1, namely we're going from 1 to 2. The height of the inscribed rectangle is 1/2. Therefore, the area of the small rectangle is 1/2. The area of the big rectangle, it's a 1 by 1 rectangle, is 1. And now what we have is that whatever the natural log of 2 is, it being the area of this region, it must be what? Less than 1, but greater than 1/2. We also know that whatever e is, the log of e is equal to 1. Well, let's go on a little bit further. What about the log of 4? The log of 4, natural log of 4, is the log of 2 squared, but we've already seen that one of the properties of an exponential function is that, of a logarithmic function, is that you can bring the exponent down as a multiplier. See, f of x to the n is n f of x. This becomes 2 log 2, and because the natural log of 2 is greater than 1/2, twice the natural log of 2 is more than 1. In other words, if log 2 is more than 1/2, twice log 2 is more than 1. In other words, if we put these three lines together, we have that the natural log of 2 is less than the natural log of e, which in turn is less than the natural log of 4. By the way, notice that since the derivative of log x with respect to x is 1 over x, and that's positive, log x is a 1-to-1 function. Therefore, if the log of 2 is less than the log of e is less than the log of 4, it follows that 2 must be less than e, which in turn must be less than 4. In other words, even with this crude approximation of just inscribing and circumscribing rectangles, I can show again, without reference to exponents, that whatever the number e is, the number e defined by the fact that ln of e is 1, that number e is some number between 2 and 4. But again, we won't dwell on this too long. What I want to do now